Okay, this video lesson is on the last gas law that we're going to look at, the temperature-pressure relationship, and this is the Gay-Lussac's gas law. We're going to start quickly with another animation, and just to see what happens when we take a gas and we alter the temperature, and we'll look at what effect that has on the pressure. So in this simulation, we can see that we have a volume of gas. It's going to be a set volume. We have a pressure gauge, and we can alter the temperature. So we've initially started the temperature at 100 Kelvin, and we can notice that the gas particles aren't moving super fast, and consequently there's pretty low pressure, about 0.2 units of pressure at this temperature. So now we're going to run through it again, and this time we're going to increase the temperature up by fivefold, up to 500 K, and we'll see what happens there. Now, by increasing the temperature, that means we've added more energy to the particles, and so if the particles have more energy, they move faster. Faster moving particles, one, collide more with the edge of the container that they're in, and two, when they do collide, they have more energy. So we can see that we've got an increase in pressure here. It went from about 0.02 up to 0.2. So a fivefold increase in temperature, in this case, gave a tenfold increase in pressure. Now we'll go up to 1000 K, and again we've added more energy. Particles are moving faster, and they're striking the surface with greater force, which is increasing the pressure. So we're up to about 0.5 units of pressure. So what we can see here happening is that whenever the pressure is increased, whenever the temperature is increased, the pressure also increases along with it. Now, if we had a volume of gas in a fixed container, like say a scuba tank, if the temperature started to increase, what would that cause? Well, we know that if temp increases, so does the pressure. And the Y is pretty simple. Temperature equals energy, more energy equals more collisions equals faster collisions. What would you rather do? Be struck by a vehicle that's moving 2 kilometers an hour, or one being driven at 20 or 40 or 80, right? So collisions can happen more frequently, but they also happen faster, which increases the pressure. And if we take, say you're out camping and you throw a can of beans in the fire, we all know to take the lid off the beans, because if we didn't, there would reach a point where the pressure is increased so much, assuming that the temperature is up high enough, that it could cause the can to explode. So mechanical containers like scuba tanks and cans, things like that, will only be able to allow the temperature of the gas particles to increase to a certain point, because as the temperature increases, so does the pressure, and at a certain point your container will fail, and that usually results in an explosion. So what does the mathematical relationship like for temperature and pressure look like? Well, it's very similar to what we saw with the relationship in Charles' law. Here we have pressure and temperature, and because they have what we call a direct relationship, meaning as temperature increases, so does the pressure, so they're directly proportional. That means that we have to establish their proportionality as a ratio of pressure over temperature. So P1 over T1 is going to be P2 over T2. If the pressure increases, so will the temperature in order to maintain that ratio. If the temperature decreases, the pressure will need to decrease in order to maintain the ratio. And remember, whenever we look at an example, whenever we would say graph a relationship like this out, if we have pressure here and temperature here, we notice that we're always going to get a linear relationship. And so we'll get a line, and because we get that line, that means that our slope is constant. Therefore, the ratio of pressure over temperature is constant. So it doesn't matter what the pressure is. The pressure divided by the temperature anywhere along this line will always give the same ratio. It will always be the same because of the fact that we have a linear relationship between these two values. So Gay-Lussac's expression of this relationship is what we see here. P1 over T1 is equal to P2 over T2. Now what we can do is look at a quick question where we put this into practice. We've got a problem here. We've got a pressure of oxygen gas is inside a canister. The canister's got a fixed volume, but this pressure is at, this gas is at 5 atmospheric units. So we know our units of pressure. And we know what our temperature is. It's at 298 Kelvin. And just like Charles' law, temperature has to be set to Kelvin. It can't be in degrees Celsius. So if you're given a question where you've got temperatures in degrees Celsius, you'll have to add 273 to the temperature to set it into Kelvin. The question asks, what's the pressure of the oxygen gas inside the canister if the temperature changes to 263? So we need to find P2, but let's quickly think about this before we even think about putting a formula down, before we think about going anywhere with it. Remember that we've got this ratio of P over T. So if my pressure goes up, my temperature must go up. Or if my temperature, say, goes down, the pressure must go down in order to keep these two things equal. So what's happening here? T1 is greater than T2. Therefore, the temperature decreased. So if the temperature decreased, then we know that our pressure is also going to have to be lower. Therefore, P1 is greater than P2. This is important to take the time to think this through before you go and attempt a calculation, just in case you alter the formula. So of course the initial formula is P1 over T1 is equal to P2 over T2. Now what we're looking for here is P2. Alright, this is our variable we want to solve for. So what I'm going to do is I'm going to cross multiply the T2 up. So P1 times T2 over T1 is going to be equal to my second pressure, P2. So now we'll solve for it, where we plug and play. So P2 is equal to P1 T1, or sorry, T2 over T1. Input our values. So initial pressure is 5.0 atm times my final temperature is 263 Kelvin, and my initial temperature is 298 Kelvin. Notice that my two temperatures will cancel out, and I'll be left with atmospheric units. So 5 times 263 divided by 298 is equal to 4.4 atmospheres. And we can see that P2 is smaller than P1, so we know we're on the right track. Now, what I've done here is given two more questions. I'm going to give you a chance to quickly write these questions out, so now may be a good time to pause them, and then I'll pull back the curtains here and show you what the answers are to these questions. And then we'll be done. The Gay-Lussac's law of relationship between temperature and pressure for ideal gases. So pause right now. Okay, now we're back. So the first question, we have a gas at 105 kPa and 300 Kelvin, and we want to know what the pressure of that gas is at 120 K. So we've reduced the temperature, and so the pressure is definitely going to have to be smaller. So we'll quickly pull back the curtain, and initially I write out all my information like we see here in a nice column. I figure out what to do with my formula, what my relationship is. Again, I'm solving for my final pressure, and I do plug my values in, and I get my final reading of 42 kilopascals. Now initially I started with 105 at 300 Kelvin. Temperature dropped by 180 Kelvin, so that's going to reduce my pressure greatly, and my temperature dropped by more than half, and we can see that the pressure also dropped by more than half. This next question here, we have a sample of neon gas. It's contained in a bulb at 150 degrees Celsius and at 350 kilopascals. If the pressure drops to 103 kilopascals, find the new temperature in degrees Celsius. So we're going to have a bunch of steps in this one. Again, initially I write down all my information. Notice that what I did right away was I changed my temperature, my initial temperature reading into Kelvin. 150 degrees Celsius plus 273, 423 Kelvin. Inputted my pressure values. Again, my pressure went down, so my final temperature is going to need to go down as well. Determine my relationship. I'm looking for final temperature here, and I plugged in my values and got my temperature, and we can see that I went from 150 degrees Celsius down to minus 148.5 degrees Celsius. So I determined first what my new temperature would be in Kelvin, and I subtracted 273 from it to get my temperature in degrees Celsius. So if you want to determine your temperature in Kelvin, you add 273. If you want to determine your temperature in degrees Celsius, you subtract 273. And this concludes the lesson on Gay-Lussac's law.